All right, we're going to be starting our lesson for Unit 9, which is all about chi-square. If you haven't already, go ahead and pause the video. Make sure that you have a calculator handy. Make sure that you have scratch paper ready, and make sure that you have your statistical tables ready, like the T-chart, that kind of stuff. All right, so what is chi-square? So far when we've been working through inference, like null hypothesis, alternative hypothesis, reject the hoe, fail to reject, when we've been working through all of these so far, we have only been looking at quantitative data. So think back to some of the examples that we've studied. We started off with one sample t-test. Remember that article that I had found online that said that there was this school in New Jersey where the seniors had applied to an average of 42 schools. Well, we might want to take that number and be curious to see if seniors at Dripping Springs High School, if the average number of college applications here is different than at that New Jersey school. So if that was your test, you would do your null hypothesis. You're comparing it to the New Jersey school. So your null hypothesis would be that the mean at Dripping Springs is the same as the mean at New Jersey, so that our seniors have an average of 42 college applications. But we suspect that the average number of college applications here is probably less than 42. So this is considered a one sample t-test because you take one sample of students and compare it to a fixed number. Some other tests that we've done, we did our obstacle course, and of course the obstacle course that we ran, we were trying to see if there was a difference between running the course with the fly eye goggles and running the course without the fly eye goggles. But since we were comparing each person to themselves, that was considered a dependent t-test. So the way we would write that is like the average difference with goggles minus no goggles. And we would say originally that we're going to go into this thing assuming that there is no difference between wearing the goggles and not wearing the goggles, but we were specifically trying to prove that wearing the goggles increased the time it took to complete the obstacle course. So again, that time it was the same group of students, one sample of students who were each running the obstacle twice. So that was a dependent t-test. Another one of the experiments that we did in class was the Amazing Race, where we wanted to compare the average time that it took to complete a maze for males versus females. So we went in under the assumption that the average time to complete the maze was the same for both groups, for males and females, but we were trying to see if maybe there was a difference in the time that it took for males versus females. Okay, so that, because you have two separate populations, was an independent or a two-sample t-test. Now, these are all t-tests and they all have one thing in common. You're dealing with the mean. When you have quantitative data, what you're comparing is the average for this group versus the average for that group, or you're comparing the mean to a fixed number. But if you're ever working with the mean and you have one sample or you have two samples, that's going to be a t-test. Well, we also want to look at percentages and compare percentages or proportions sometimes. And when you deal with categorical data, you cannot use a t-test. That's where you use something called a chi-square test. And that's what Unit 9 is going to be about. Unit 9 is going to be all about categorical data, setting up a null hypothesis, alternative hypothesis, running the actual test, and drawing a conclusion on it. The biggest difference is you're not going to use your t-chart. You're going to be using the chi-squared chart and the formulas that go along with chi-squared. All right, so here is what the chi-square distribution looks like. Notice that it's not symmetric. It doesn't look like the normal curve. It doesn't look like the t-distribution. It is right skewed. And one note is that it only takes on positive numbers. So it starts down here at 0 and goes up from there. So it's skewed right. It is described by its degrees of freedom. So degrees of freedom, if you look at the chart here, so this is past your t-chart, it's the chi-squared table that I'm looking at right here. When you read your chi-squared table, you have degrees of freedom on the left-hand side, and then you have your probability on the right-hand side. So using the chart, if I asked you to find the critical value for a significance level of 0.05 with 4 degrees of freedom, I would go over here to 4 and 0.05. That gives me a chi-squared critical value of 9.49. Same thing, you could find the critical value for a significance level of 0.01 with 7 degrees of freedom. You would go to 7 degrees of freedom and over to 0.01, and that would be 18.848 for our critical value. Now, you don't have to worry about two-sided tests when you do chi-squared because it's not a symmetric distribution. It starts at 0 and only goes to the right. You can never have a two-tailed test. So you don't ever have to worry about cutting that significance level in half or anything like that. Whatever you see is what you get. There's 2 types of chi-squared tests we're going to study in this unit. The first that we're going to be taking a look at is the chi-squared goodness of fit test. In the next video, we will cover the chi-squared test for independence. All right, chi-squared goodness of fit test is when you have one categorical variable, and basically you want to know if the data you have produced fit with some hypothesized distribution. Your null hypothesis, you know how we've always written the null hypothesis with an equal sign? So you're basically doing the same thing but in words. Like the equal sign means same. So what we would say for our null hypothesis is the population distribution is the same as the proposed distribution. In our alternative hypothesis, we're always trying to prove that there's some kind of difference. So our alternative hypothesis would be that the population distribution is different in some way than the proposed distribution. The new formulas for this unit, this symbol right here, that is the chi-squared symbol. That's the Greek letter chi and then obviously squared, so chi-squared. To find the chi-squared statistic, you take the sum of the observed values, so whatever you observe when you collect your data, minus what you expect based on your null hypothesis, squared over your expected values. Degrees of freedom is a little different here. We're used to doing n minus 1 as in the number of observations or the number of people in your sample minus 1. Here it doesn't really matter the number of people because we're dealing with proportions. It's actually the number of categories minus 1. All right, so let's take a look at an example here. Does the data suggest that the ethnic distribution of traffic stops is different than the ethnic distribution of all Austin area drivers? All right, so we see here data that's collected, I guess, from the DMV. I don't actually know if this is real data or not. It looks like 70% of all Austin area drivers are white, 7% black, 19% Hispanic, 3% Asian, and 1% are classified as other. And then when you look at these traffic stops, what we observe from our traffic stops is that 97 drivers were white, 27 drivers who were stopped are black, 57 Hispanic, 4 Asian, and 7 others. So what we want to know is there a difference between what we observe in the traffic stops and what the percentage is for all Austin area drivers? So you're always going to go under the impression that there is no difference, that these two are the exact same. So we're going to assume that the breakdown for traffic stops is the same as the breakdown for all Austin area drivers. Now, that's why we call this goodness of fit. How good does our data that we collected fit the given distribution? Now, the alternative hypothesis, you're trying to prove that there's a difference. So we want to know, is the distribution for traffic stops different than that of all Austin area drivers? So let's crunch the numbers here. We have what we observed in our actual data, and then we know what the percentages are supposed to be. What we need to calculate next is what we expected those numbers to look like. So I need to get my total. I'm going to add these together. 97 plus 27 plus 57 plus 4 plus 7 gives me a total of 192 traffic stops. And out of those 192 traffic stops, I expect for 70% of those drivers to be white. So I'm going to do 0.7 times 192. So 70% of 192, I expect for 134.4 of those people to be white. And then I expect 7% to be black, so 0.07 times 192. 0.07 times 192, 7% of them, that would be 13.44 black individuals. Hispanic, we expect 19% of the people pulled over to be Hispanic. So 0.19 times 192 is 36.48. And then 3% of 192 is 5.76, is how many Asians we would expect. And then 1% of 192, 0.01 times 192 would be 1.92. So just eyeballing these numbers, does it look like it matches what we expected it to be versus what it actually was? Some of them look pretty close. You know, the Asian population, we expected there to be 5.76 Asians pulled over. There were actually 4. Others have a little bit more of a gap there, but is that just a coincidence or is there something significant going on? That's what we're going to do as we finish out this test. So I'm going to come over to the last column and we're going to calculate our chi-squared values for each one of these ethnic categories. So this is going to be the observed value minus the expected value squared over the expected value. So this first one would be 97 minus 134.4 squared over 134.4. And I'm getting 10.4. I'm just going to use one decimal place here. All right, the second category for the black ethnicity here, we're going to take the observed values, 27, minus the expected values, 3.44 squared over 13.44. So observed minus expected squared over expected. 27 minus 44 squared over 13.44. All right, I'm getting 13.7. All right, moving right along. For the Hispanic group, we've got observed 57 minus expected 36.48 squared over 36.48. $11.5. For the Asians, we've got 4, our observed value, minus 5.76, our expected value, squared over 5.76. That is 0.5. And then last, for the other group, we've got 7 minus 1.92 squared over 1.92. It's 13.4. All right, now let's talk about what these numbers actually mean here. The way we're calculating them is by taking the observed value minus the expected value first. Basically, it's telling us how big is the difference between what you see and what you expect. In fact, if the observed values and expected values were identical, your chi-squared value would be 0. So the bigger this chi-squared value is, the bigger the difference in those categories. So like notice the Asian group right here, their chi-squared value is very small. It's only 0.5. That's because there wasn't much of a difference between what we observed and what we expected to get. But if you look at the black population or the other population, these have very high chi-squared values because what you observed is very different than what you expected to see out of that traffic stop. So let's go ahead and do our calculations here. My chi-squared statistic, the whole statistic, all I need to do is add these numbers up. So I'm adding together all of those individual chi-squared values to get the total. So 10.4 plus 13.7, 11.5, 0.5 plus 13.4. So I'm getting a total chi-squared value of 49.5. Now, that's where I stand. That's based on my data. What I need to do next is look at my chart and figure out where my cutoff is. So this is going to be based on degrees of freedom. So degrees of freedom, remember, is the number of categories minus 1. I'm looking at 1, 2, 3, 4, 5 ethnic groups. So 5 minus 1 is 4 degrees of freedom. Okay, so looking it up on my chart, if I use a significance level of 0.05, since that's what we typically use, if I do 0.05 with 4 degrees of freedom, that gives me a chi-squared value of 9.49. Now, picture what that looks like. I'll draw it up here at the top. Picture what that chi-squared value looks like. You have your chi-squared curve, which is right skewed. The curve begins down here at 0. If I draw 9.49 on this curve, that means that from here all the way up is a probability of exactly 0.05. Okay, now from 9.49 all the way up is exactly a probability of 0.05. Well, where does 49.5 fit on that curve? So think about going way out here and it gets tiny, 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 tiny. That's 9.49. 49.5 is going to be way, 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 way down here. Now, if the probability from here down is 0.05, that means the probability from here down is tiny. So P equals tiny. It's a very low probability. And what do we say? When P is low, reject the hoe. So we reject the null hypothesis, which remember the null hypothesis is that the distributions were the same. We were trying to prove that they were different. So if you reject the null hypothesis, that means you have enough evidence to prove or conclude that the distribution of traffic stops is different than the distribution of all Austin area drivers.